Hi everybody and welcome back. This is homework 942 and this is problem number 2. Here we're dealing with conservation of energy and some non-conservative forces and work done by non-conservative forces. And we're going to be dealing in this problem in particular with two non-conservative forces. One that puts energy into the system and one that takes energy out. Okay, so we've got a car going up a hill. All right, so I'm going to draw the car over on the far right here. So here's our hill, here's our incline, and that hill is, what is it, 16.2 meters in height. All right, so that'll help us a little bit later on. Here is our car, and here's our car at the top of the hill right here. So we have an initial and a final position. Okay, so energy initial, energy final, and we have some non-conservative work that is done in the in-between. Okay, so what kind of non-conservative work is happening right here? Well, we have a non-conservative force due to friction. All right, friction is going to be robbing the system of 3.11 times 10 to the fifth joules. All right, the engine, which is, even though it's kind of inside the car, it's considered an outside force. That is, it's getting its energy from somewhere else, namely gasoline. But so the energy is putting the engine, is putting energy into the system to the tune of 6.44 times 10 to the fifth joules. All right, so I'm going to write them down below right here. I'm going to call this non-conservative work due to friction. So I've got a subscript to a subscript. That is negative 3.11 times 10 to the fifth joules. And we got non-conservative work done by the engine, and that is positive 6.44 times 10 to the fifth joules right there. Okay. So the question is, what is the change in kinetic energy from the bottom of the hill to the top of the hill? All right. Well, the best way to do this is to establish what kind of mechanical energy the car has at the top and at the bottom of the hill. All right. Let's see, I'm going to, just so these stand out, I'm going to write these in red. So at the bottom of the hill, is it possible that it has kinetic energy? Sure. All right. Kinetic initial. It's possible that it's moving. All right. It's also possible that it also has some potential energy as well. All right. Even if it's zero, it's got some kind of potential energy. At the top of the hill, it's got some kinetic energy final. All right, and it's also got some some potential energy. Where are we? Potential energy final as well. Hopefully you don't hear that printer in the background. My wife's printing and it's making a kind of a racket. So all the mechanical energy initial can be summed up as kinetic initial plus potential initial. All the mechanical energy final can be summed up as kinetic final plus potential final. And then we have all this added non-conservative work in between. So here is kind of our working equation that we're going to start out with. Mechanical energy final equals mechanical energy, all the mechanical energy initial, plus any non-conservative work that is done. All right. Well, in this case, we've got two non-conservative works that are done, so let's just go ahead and write them. Our energy final equals energy initial plus, I keep putting my wrist on the bottom right here. All right, sorry about that. Plus non-conservative work due to the friction and non-conservative work due to the engine. All right, so this is a negative value. This is a positive value. We're just going to leave them as is for now because we're given what those values are right here. There's that, and then there's this. But we're not going to plug them in quite just yet. First of all, we need to solve for what we're actually being asked to solve for. What are we being asked to solve for? The change in kinetic energy. All right, well, then that means we better start, if we want the change in kinetic energy, that is delta K, we better start stating the mechanical energy in terms of kinetic energy and potential energy. All right, so like we said before, finally, how can we, that is at the end, final, how can we state the mechanical energy total? Well, that's kinetic final plus potential final, right? That's all wrapped up in there. And the the mechanical energy initial is kinetic initial plus potential initial, right? So if everything stopped right here, then that would mean everything was conserved, and so we'd have the same amount of energy finally as initially. Well, it doesn't happen because we have these non-conservative forces. In fact, I'm going to go ahead and write them in. Plus non-conservative work due to friction, plus the non-conservative work due to the engine. Okay, remember, we are solving for the change in kinetic energy. Change in anything is always final minus initial. All right, so we have the final over here already. I'm going to change colors right here. I'm going to subtract to move this kinetic initial over here. And I'm going to also subtract to move this potential final over there. So we should have something that looks like this. Kinetic final minus kinetic initial equals everything else. That's potential initial minus potential final plus the non-conservative work due to friction and plus the non-conservative work due to the engine. Okay, finally, we have this in the form that we want. We want that right there because we really care about the change in kinetic energy. So that is that right there. Now, all it needs to be done is to plug in everything we know for these right here. And then we have a solution for the change in kinetic energy. All right, what's the nice thing about potential energy? That is, we can set 0 wherever we so desire. So why don't we call that down at the bottom right here? Why don't we call this base level 0? So that means that potential energy initial can become 0 and go away. And all that we have left is our potential final. So it's a minus potential final right there. So we're just going to put minus, how do you find the potential at any one point, at any one height? That's mgh, okay? Plus, now we're ready to put in our non-conservative forces. What's a non-conservative force due to friction? I'm going to put this in parentheses, plus a negative 3.11 times 10 to the 5th joules. That's how much energy friction robs from the system. What about this non-conservative work due to the engine? Well, that's a positive, plus a positive 6.44 times 10 to the 5th, joules that the engine puts into the system. So that's that, and that is that right there. Okay, all that's left to do now is plug and chug. Oh, okay, well, we did that already with the non-conservative forces. I got to plug in my values for mgh. We can't forget that this is a minus out front here. That's going to make all the difference, all right? Equals minus, what's the mass of the car? 1250 kilograms. G is 9.81 meters per second squared. We know that. The height, what's the height of the hill? Well, the car rises through a height of 16.2 meters. 16.2 meters. That's an M there at the end right there. 16.2 meters. Okay, so that's a minus out front. Can't forget the minus. Plus negative 3.11 times 10 to the 5th joules. Plus a positive 6.44 times 10 to the 5th joules. Now all of our values are in place. Now all that's left to do is to plug and chug. And I get 1.34 times 10 to the 5th joules. And if we do our decimal moving, that comes out to 134 kilojoules, or 134,000 joules. So either way you say that, that's all pretty much the same thing. All right. The important thing to remember is to watch your signs. All right. This final potential energy was a minus right here. This work due to friction was a minus, and this work due to the engine, this positive work due to the engine, was positive right here. The first time I did this problem, I have to admit, I missed a sign, and I got the wrong answer. All right, so I went back and checked. Check your signs. Make sure all your signs are right. Then when you plug and chug, you should be in good shape. So there you have it. That's problem 2 from homework 942, and the answer is 134 kilojoules. Thanks for following along. I'll see you on the next one.